Hi, I'm Nikhil. I'm a PhD student in neurotechnology at the University of Manchester, and I'm supervised by Alex Kazin. Today, we're going to talk about a smartphone app for brain stimulation. So, first, the presentation will be divided into two bits. The first bit would be about open loop stimulation, and then closed loop stimulation. So, first, open loop. This is essentially stimulating without feedback from the brain. One of the more popular ways of doing this is using currents, and these have been either be it non-invasive or invasive, and has been used in applications like Parkinson's, memory, sleep, and etc. But one of the main problems with current stimulation is that they are not very portable. The equipment's large and clunky, and not ideal for out-of-the-lab use. And what we're interested in is in technologies for out-of-the-lab use that are portable. That's why recently people have been looking at stimulation like lights and sounds that you can use to essentially affect brain activity. And the advantages here is that lights and sounds are a more natural stimuli. Currents, we're not exposed to currents every day, but lights and sounds, yes, we are exposed to it every day. And more importantly, they are more portable as they could be delivered by, say, a smartphone. So the first kind we'll look at is binaural beats. This is auditory stimulation, and these are essentially tones of two different frequencies provided to each ear separately, and the brain waves essentially synchronize to the difference frequency. For example, say you provide 400 hertz to one ear and 410 to the other, the brain waves will synchronize to the difference, which is 10 hertz. And this has been used in applications like improving working memory, inducing sleep quicker, reducing stress, pain perception, and improving creativity and divergent thinking. So what we wanted to do was implement this on a phone. So we created an Android app which does not have pre-recorded audio and just loop through that. Instead, we generate the samples in real time, cycle by cycle, and embed a phase accumulator so that we could avoid any discontinuities in the signal at frequency transitions. And we present this app could provide frequencies in the 0 to 20 hertz range, and the test results are shown on the right, x-axis desired frequency and the y-axis measured frequency, and as you can see, fits perfectly well and it works. So that's the auditory stimulation in the app. Next, we move on to visual. This is a bit, so these are essentially flickering lights via the phone, and you could change the frequencies of the flicker. And this has been used in applications like reducing pain perception, anxiety, sleep, and attention. Implementing this on a phone is a bit more challenging than the audio case, mainly because of the refresh rate limit of current phones. For example, the phones we used has a 60 hertz refresh rate, and what that means is not all frequencies are presentable, but only the ones that are integer divisors of the refresh rate. For example, 10 hertz and 30 hertz fine, but 11 hertz, 9 hertz, you can't. It's more challenging. So to overcome this, what we did was we used an interpolation algorithm where they essentially interpolate they provide at certain frames intensities that are intermediate values. So and overcome to provide a good approximate of a square waveform. And to overcome that challenge, and then with this we were able to provide again frequencies in the 0 to 20 hertz range, and you can see again test results on the right. It works. So finally, this is what the app looks like. Homepage, left the audio, right the visual, and that's the open loop neuromodulation. Next, we move on to closing the loop between sensing and actuating the brain. So why do we want to close the loop? Mainly because of variability. One of the main problems with open loop stimulation people have found is that the results are very variable, both in therapeutic outcomes and experimental results. And this is mainly because of the hit and miss approach done with open loop stimulation. And because of this, you also get side effects due to unwanted build-up, unnecessary stimulation at different brain regions. And also closed loop stimulation platforms could help with experimentation and finding the right biomarkers. and ultimately providing a more personalized brain stimulation tool for each user, as every one of our brains are different, so we would each need a different stimulus protocol. So that's the why of closing the loop. And in terms of the application that we're looking at, the clinical driver is sleep engineering. So essentially here, groups have found that if you provide auditory tones at very precise times of the slow oscillations, which happens at stage 4 of sleep, you could strengthen these oscillations and in a sense improve memory consolidation. So that's what sleep engineering is. So our platform, we have to sense the brain activity first using EEG, and then extract the slow oscillations, and then extract the phase in real time quickly, and then at the right time, at the right phase, play the auditory tone. So the challenge here is mainly, one of the main challenges here is extracting phase in real time, because the brain waves are not oscillatory, pure oscillations, but very noisy and non-stationary. So to extract the phase in real time, we used a technique called the phase lock loop. Essentially, on the right you can see it actually has a phase detector which measures the phase difference between the input signal, which is the EEG, and the reference sinusoid coming from a voltage control oscillator. And the phase difference is noisy, so it gets filtered out to get the DC component, and that provides a nice control signal to the VCO, which feeds back to the detector. So in this way, essentially what you need to know is that this extracts the phase of an incoming signal in real time. The advantages of using this as opposed to a Fourier transform based technique is that it operates sample by sample, not on chunks of data. Hence, it's low latency and very quick. And because it does not operate on a chunk of data, there's no edge artifacts, it's adaptive, robust to noise, and computationally very simple. So that's the algorithm we used. And the results, so this is data from about 15 subjects' sleep data. So we ran the PLL and extracted the phase offline. And here's the phase error plots. And as you can see, measured both on a PC and a phone. And we get a 14.8 plus minus 38 degrees phase error. Phase error here is measured by phase extracted using the PLL and the gold standard, which is Hilbert. And we also get a computational cost of 0.04 plus minus 0.2 milliseconds on a phone. So that's good results, and it compares. It's very similar to the state of the art, where they have used similar techniques on lab-based platforms and got similar phase errors. But our differentiation is not really in the use of a PLL, but doing all of this on a smartphone eventually. So that brings us what's next. That brings us to what's next and the future plans. And essentially, we have to tie all these different bits together: the stimulation, the feedback, the signal processing, and the sensing to complete the loop and test and characterize that platform. And again, like I said, we're targeting the sleep engineering application. Here are the image references that we used, and thank you for listening. I hope you enjoyed it.